Good day to all of our petroleum industry colleagues. I hope everyone is safe and sound. My name is Numan Mana. I'm a petroleum engineer currently working with Halliburton, Iraq. On behalf of Arab Oil and Gas Academy, I would like to welcome you all to the third session of Dr. Hatem Farouq Ewida. Dr. Hatem Farouq Ewida has worked extensively in oil and gas industry in both technical and managerial positions with local and international companies such as JEPCO, British Petroleum, and currently with Perenco, North Sea Petroleum Company, where he is the exploration general manager and board member of its JV. He received bachelor diplomas, master and PhD degrees in geology, petroleum geology, and geophysics. Dr. Hatem has taught industry-tailored and university courses, as well as published and reviewed several research papers with local and international journals. In addition, he supervised and referred many PhD and master programs. He is a board member of the Egyptian Physical Society, EGS, an active member of SEG. Now, the third session is holding the title of Overview of Seismic Data Processing. Before we begin, just to make things clear for all of you, Dr. Hatem will record your question and will answer them in the end of the lecture. Also, you should write them in the Q&A box down below. And so now we shall begin this session. Welcome, Dr. Hatem, again. It's a pleasure having you here today with us.
Thank you, Loma. It's my pleasure to be with you.
Thank you.
Hello, everyone. I wish you all are doing well. Today, we are going to talk about a very important subject, actually, in the seismic exploration method, which is the seismic data processing. Actually, we will spend around an hour, so it's an overview. Seismic data processing is a rich and wide subject in the seismic, and you can read books actually in seismic data processing. So I'll try to simplify as much as I can. Lecture today, or our talk today, I will give you a quick introduction, and then I will give you talk about the definitions and principles. Then I will identify to you the signal and noise, following by the seismic processing flow, either pre-stack, post-stack. I will talk about, we'll show you some real data examples, actually, covering most of the processing routines or processing steps that I will cover today. So as you know from my previous lectures, is that the seismic method, to apply seismic carbon exploration, we passed by three main stages. These stages are the seismic data acquisition and the seismic data processing and the seismic data interpretation. And today we are going to talk about seismic data processing. So we'll start with some definitions and the principles. We'll cover why we perform seismic data processing, what is a seismic trace. We talked about this before, but I will add some more information for you. This will be followed by the seismic processing basics, basic seismic processing functions, seismic domains, and we'll end this part by the sorting and gathering domains. So why perform seismic data processing? The seismic data processing is the second step in seismic method exploration, And I just mentioned it's in the middle between seismic acquisition and seismic interpretations, and it's responsible actually for increasing the signal to noise ratio. So it attempts to enhance the signal and diminish the noises. We will understand what are the differences between signal and noise soon. So it has to, or it enhances the signal to noise ratio of the seismic section. Seismic section is the final product of the seismic processing or the seismic method as a whole, and to remove some noises or decrease the noises and remove the artifacts that has been recorded with the signal. So the end result should be a more interpretable section. To understand what I mean by more interpretable section, so in seismic interpretation, we start from the conventional seismic interpretations. As you see here, you see these are two different vertical seismic sections, and it have interpretation. So you see different layers with different colors here, and you have faults. This is what we call the stratigraphic and the structural interpretations, or this is the conventional type actually of seismic interpretation. We can also extract some seismic attributes to see, as you see in this picture on your right-hand side. This is sort of a channels in the subsurface, and this is extracted from the seismic volumes, which is the reflectivity as you see on this conventional seismic interpretation. Also, we can invert the seismic data and convert this seismic reflectivity into lithology and the fluid distribution, as we mentioned before, and our next lecture will cover more the advanced seismic techniques. So what is a seismic trace? As I mentioned, we talk about this twice actually in the introduction and in seismic data acquisition, but I want to add to you and remind you with what is a seismic trace. So if I'm acquiring seismic data with a split spread design as you see, so I have the source in the middle and I have several receivers on both sides of the source. This source, the nearest receiver distance, we call it the near offset, and the farthest receiver distance, we call it the far offset, and in this split spread, it is in both sides. So if I have this geologic section in the subsurface, so I have, as you see, 4 different geologic units. You can see the different velocities. V means the velocity of sound within this lithology. So you have different velocities and you have different thicknesses, actually, as you see. So as I have 4 successive rock units, I will end up with 3 interfaces, interface A, B, and C. So let's see what happened when we acquire this data. So for the first interface, I will have I will receive reflections from it, as you see, like this in the red color, and from the second reflector, we will receive another reflection, and so on from the third one. And as this is a split spread, you will have this recorded on the other side from the source. After we record this and we do, for example, the first processing step, we will end up with a seismic record, as you see. This is a seismic record, and you can see here, you can notice here, these are the 3 reflectors will be plotted like this, and it has this sort of curvature or hyperbolic shape. And the trace that I use or the receiver that I pick here, which is the third one from the source in both sides, you can this will be plotted with this type of traces. So we call this is a trace. So you know now that this trace represents the reflection for only one receiver for the seismic trace. So this is another shot record, but this is, we called it the off end or end of, which is mainly of marine recording. You can see here the traces. So each trace on this was recorded in one of the receivers that you see these blue triangles, and the source was here in this side. This axis is a two-way time, and here you will find the source receiver offset or the channel numbers or the receiver numbers on the x-axis. So this is in the field records. Field records means this is exactly as I record the data in the field. This is the geometry of the field recording. But after I finish the processing, I end up, as I just mentioned, with a seismic stack section. And this seismic section also have traces. It's built up of traces, trace beside trace beside trace. But the trace here is generated after the last step in the processing, which we call the stacking. And this stacking give me this trace as if I record this trace on the field where the source and receiver were on top of each other. We'll understand how this comes. Okay, but this is called the trace if it is in the records or the field records or a trace in the seismic section itself. So what are the basics of seismic processing? So we mentioned before that seismic processing is responsible, or the meaning was like this, is responsible for purifying seismic data from all noises, and noises are the unwanted energy. Okay, and increase the signal to noise ratio. Signal is the wanted energy. Which energy, what energy we are talking about? This is the sound energy. And which sound energy? The sound energy that we send from the surface, from the source of the rock, as we mentioned before. So if you hear my sound now and you have like a nearby other sound, you will hear both of them. But one of them, which is my sound, is the signal to you because you want to listen to that, and the other sound will be the noise. So in seismic processing, it is responsible for purifying the seismic data to end up with more signal than noise. So in seismic processing, if we have like this, again, geometry, split spread geometry, which reflect more a land seismic acquisition, this data, as you know from the acquisition, will be recorded on magnetic tapes with the field format, like if you remember SEG-A, SEG-B, SEG-C, SEG-D, or SEG-D, okay, and from these tapes, we'll take these tapes to the processing center, and at the processing center, these tapes will be read, which will be dumped like this. And if you remember, this is a digital recording, so these digits represent the reflections, okay, and then the software will change this by a processing step called demultiplexing, return it back to the analog plotting or the traces. As you see, this is the record. So we start from recording. From acquisition, we record the data on sort of media, which is mostly magnetic tapes, and then we return back in the processing and demultiplex processing software format. And after doing several steps in processing, we end up with vertical seismic section if we do 2D, or a volume of data, as you know from the acquisition, if I'm acquiring 3D. So this is the basics. This is how the processing goes. So what are one of these main 4 functions? The first one is editing and applying some fundamental corrections. We will go through everything in details now. So I'm doing some editing. We will understand what meant by editing, and do some fundamental corrections. Then we try in the processing to enhance. These are the seismic processing basics. We have the acquisition in the field, and the data is recorded into a media, which is mainly the seismic field tapes or magnetic tapes, which has recorded in, or which recorded in digital format with standard format like this SEGA, B, C, or D. And in the processing center, we start to reformat the data to the processing software to work on enhancing the signal to noise ratio. This is how, if you dump the seismic tape, you will end up with these numbers, which is a digital, and then you process the data, will see the field record, apply some steps, and reach the seismic stack volume if I'm acquiring 3D, or the seismic stack, vertical stack section, if I acquire 2D. So 4 main functions for the seismic data processing. We will talk about each of them in details, but we'll know them first. So the first one is applying some editing and fundamental corrections and enhance the resolution in time, try to enhance signal to noise ratio, and enhance the resolution of seismic data in space. To understand these functions, and we will go for each one of them in details, but to understand that if this is the first record after, this is a field record just after one step in the processing, if we try to edit, to make editing and some corrections, we will apply a step called gain recovery. We'll talk about it in details. So this data is before the gain recovery. Here is, you find it after gain recovery. So before gain recovery, you can see the reflections clearly, but after we apply one step, which is one of the fundamental corrections, which is the gain recovery, we start to see some reflections in the data. This example shows some corrections. One of the corrections we call the static correction. So if you see the data within this red circle, you will find the reflector has a sag or a sort of synclinal shape, but this is not true. But after corrections, this is how it looks. There is no any synclinal shape, but from where this comes, we'll understand when we talk on the step of static corrections. Also, further to that, we'll have some enhancement in the resolution in time. You see that the reflectors now appear more clearly, in which we apply a step called deconvolution. Again, we will talk about this in more details. And then we try to enhance the signal to noise ratio. If you see, this is part of the vertical seismic section. You see a lot of hashers. You can see some reflections, but they are not continuous. You cannot follow it across the whole section. But when we increase the signal to noise ratio, you see how clear is the section appear now. To enhance the data in the space, we use what we call the migration. So if we take a look on this sort of reflectors, you have 4 reflectors here, and they have what we call bow tie. We don't have this shape in geology. So this is something related to the seismic data acquisition. It needs to be corrected. When we correct this or enhance the data in space, it looks like this. So here it is a syncline. It's a syncline, geologic syncline. Okay, it will appear like these bow ties in the uncorrected or in the time seismic data. So going to the domains, what we mean by domains? To simplify this domain, if you think about water. So when we drink water as a liquid, okay? But you can change the status of the water from liquid state into solid state by freezing, and you have ice, okay? And you can change the water from liquid state into vapor state or gaseous state when you boil it and it converts into vapor. So all are water, okay? But you can find the water or convert the water from state to state. This state in seismic we call the domain. So the seismic data I can plot the seismic data or represent the seismic data in different domains. The famous ones that I showed you the examples about them since the beginning, this is what we call time domain or TX domain. Why we called it like this? Because it is plotted against time. So it's called the time domain. So this is a time domain data, which means that the data is represented in the time domain. The vertical section is the two-way time, and here the horizontal the horizontal axis will have either the receiver number or the offset or whatever. So the distance, the x. Okay, so this is what we call the time domain. This data I can change it or plot it in a different domain. The most simplest domain is the frequency domain. The frequency domain, which is I give the sample f here. So if I change this data into the frequency domain, it will be plotted in either in both actually the frequency amplitude domain, or what we call frequency domain or amplitude spectrum, and the phase spectrum. So it will be presented in an amplitude spectrum, which is this curve that you see here. Okay, this curve, you have the frequency on the x-axis and you have the amplitude in the y-axis, and this curve represents the amplitude and the frequency of this data. And the phase of the data also can be plotted. And to understand what is this zero phase means that the wavelet or the wave is symmetrical about its zero axis. So this is the data. This, what you see here in plots in curves, are the data that you see it in the time domain. So this domain we call it the frequency domain. How I can go to the frequency domain? The scientist called Fourier, he had the Fourier transform, so he can change the data from the time domain into the frequency domain with what we call 1D forward Fourier transform. You can do whatever processing you need and then convert the data back into the time domain using the inverse Fourier transform. So this is, remember, a 1D Fourier transform or a 1D frequency domain. Another domain, which is also in the frequency domain, but in this case, we convert the data into the frequency domain, but plotted the data into two different axes, which is not the frequency and amplitude. It is now the wave number and frequency. So wave number against the frequency, which we called it the FK domain. So the FK domain is a frequency domain, but we plot the data into the FK graph as you see. The importance of this domain is that the data can be separated according to their depth. So if you take a look in this one on your left-hand side, you see the reddish reflector here. It is nearly horizontal. Because of that, it will be represented on the middle axis on the FK plot. But you have another two reflectors that have different depths. One of them had a linear depth, which is a blue one, and it will be represented in this area as a line. But the hyperbolic green reflector will be represented with this triangle on this side of the FK plot. So again, this is called 2D frequency domain, and in this case, also we use the Fourier transform, forward Fourier transform, and then when we finish processing, we return back to the inverse Fourier transform. So this is a real data example. You see the record here, and you see this is the record. If you see my cursor, and here is the FK plot. So you see how the data distributed in the two different directions. So the data in the FK domain, which is one of the very effective processing filter, the data is separated in this domain according to their depth. So going to another domain, which we called it the tau B domain. P is the slowness, which is 1 over velocity, and the tau is the intercept at the 0 offset. And in tau B domain, we have 2 different conversions. One of them is linear, and the other we call it parabolic tau B. In the linear tau B, if you have this cartoon of which contains 3 different reflectors, or 3 reflectors with different depths, red, blue, and green, when you convert this data into the tau B, the linear tau B domain, it will be represented as we can say points, as you see here. So you can separate the data according to their depth now by 2 different domains. One of them is the FK, if you remember, and the other one is the linear tau B. Also, the parabolic tau B domain will discriminate the data according to their velocity. So if you have here like the reflectors, the blue reflectors, okay, and you have some red reflector, okay, below each one of them. If I go to the parabolic tau B domain, I can separate the red reflectors will be plotted in some area and different than the reflector, so I can separate between both of them, and this is a real data example of this. Okay. So these are the main domains that I want to tell you about. There are another meaning of the domain, or we mean other type of domains, which is depending on the sorting of the traces. So I can sort the seismic traces in different gathers. I can gather the traces in different domains, for example. So the data as acquired in the field, this is what we call the short domain data. This is the short domain data, or the field record. So the field record of the short domain data is exactly has the same geometry of the acquisition. Okay, but I can sort this data. I can take, for example, this is if I have an off end for the marine. I can, for example, take the common midpoint trace, if you remember the acquisition. So I can gather all the traces that comes from the same subsurface point into a gather. From where I get this gather, I collect that from the field record. So I can sort the field record into CMB or CDB gathers. Also, I can sort the data into a common receiver, as you see. So I can take the traces. It means that I collect all traces that recorded by the same receiver and put it together in an ensemble, as you see. Okay, this is what we call, this is what meant by sorting. So this is a common receiver. So the common source, which gather is the common source? Yes, it is the field record, or how can I record the data in the field? Okay, so, and also I can gather all the near traces together, or all the far traces together. Of this gather has its own importance. For example, the field record, as we mentioned, or the short record, or the common source record, the 3 are the same, are how the data was acquired. So I can know where is the position of the source, where are the other traces. And some noises I can attack on this domain. But the CMB gather, for example, is the most important gather, because this is our method. If you remember our acquisition technique, which is the CMB technique, okay? For example, the common receiver gather, we can attack certain type of noises, unwanted energy. For the near trace and far trace, I can check my geometry. Do I use the geometry right as I acquire the data or not? You can notice that, you can see that far trace means that the reflection, the first reflection, came at later times than the near trace. So again, to go further, so all the data before the stacking, which is gathers like field gathers, CMB gathers, comma receiver gathers, whatever. This is what we call the pre-stack gathers or pre-stack domain. And when I stack the data and want to apply some processing on the stack, we call this is a post-stack domain. So the stack section, what you see on your right-hand side, this is the final product of the processing. And at this section, only you can talk in geology. Okay, you can talk geology in this stage only. So let's understand what are noises and what are signals. What are the difference between signal and noise? So generally speaking, signals are the wanted reflections, which comes from are coming from the reflectors, the geology, which reflect geology. This is a signal. These are the wanted energies. Unwanted energy is anything other than that. Okay, so we'll cover the noises, the type of noises to see the difference between signal and noises. We'll talk about the coherent and random noises. We'll give examples about the swell noise. We'll talk about the multiples. We'll talk about how this noising affect the stack. So if you take a look on this record, it's actually one record, but it is a mirror image of itself, and I put them beside each other. Please take few seconds and try to figure out where are the signals and where are the noise. Okay, so if you take a look, you will find different dipping reflectors. Okay, so this nearly flat reflectors, which has a hyperbolic shape, these are the signal, the major reflectors. But you can have refractions in the shallowest part. You can see the air wave, for example. You can see the ground roll. So all of these are noises. We'll understand what meant by each of them and how I can get rid of each of them. So this is how the noise looks and the data, or the signal versus noise. So let's understand what's coherent and random noise to understand what you hear in the industry. So the coherent noise are those unwanted seismic energy that shows the same phase of the data. So it is found with the data itself. Okay, so it have consistent phase with that from trace to trace. So it is with you like the data. You can see it everywhere. For example, a type of noise we call the ground roll, type of we call the multiples, which is one of the very dangerous type of noise, and the airwaves. The other type of noises is random, and from its name, it doesn't have like a certain shape or it's not in phase with the data, and it is simply we can get rid of it by very simple processing steps. From where this random noise came, it came from the activities while we acquiring the seismic data. So let's see some examples. So if you take a look on this record, this is a field record. Okay, you can see ambient noise, which is a random noise. You can have electric current noise, as you see. You can see the ground roll, which is one of the coherent noise, and you can see source generated noises. Okay, so what is the ground roll? Just because we mentioned it several times, this is the surface waves. These are the surface waves that that do not penetrate the ears. If you remember, we have two types of waves: the body waves and the surface waves. So this is the surface waves that propagate on the superficial boundary, so it doesn't have geological information. Okay, so this is how the noises looks on the data. Let's take one by one and understand more how these noises looks. So we'll see an example from the coherent noise from one of the most what I mean very bad type of noises that cause headache actually to all geophysicists, which are the multiples. You remember the bus of the data that we need to record, which is going from the source to the geologic reflector or interface and back to the receiver. This is what we want to record. This is what we call the primary reflection. But any other pass, as you see from this figure, what you see here is this is a cartoon for a marine wave ray pass. So you have the sea at the top, and then you have like this is the sea bed or the sea bottom. You have some geological layer here, you have thin sedimentary layer here, and you have a deeper reflector from another geological layer. So if what's in yellow is the source, which we call shot sometimes, and in green are the receivers, and these lines is the ray path. So the rays that take what I mean, it fluctuated in the water before going to the reflection point and get back. This is, imagine any what I mean ray path regime you can find in the seismic data. If you remember when I mentioned that seismic data goes everywhere, so you can have reflections from everywhere. So how I can what I mean recognize these multiples on the seismic data? If you take a look on this seismic section, a beautiful seismic section actually, and this is in the marine seismic section, so is the seabed. So you can see the seabed reflector here in the yellowish color. Okay, you see this blue reflector here. It's a multiple. It's not a real data. So multiples is like the echo. It's like the echo. You know, you hear your sound several times. This is the echo, and because of that, here the seismic data records the seabed reflector, and then the echo of it came later in time, and it has the same shape as you see. Okay, but it is double the time, and also it is what I mean twice the depth. So it came at twice time and double the depth. If you take a look on this, so this is that the multiple follows the same topography of the seabed. So please compare between this blue reflector and the yellowish reflector in the front. Okay, this is unreal reflector. It is not there anymore. It is not there. It is just an echo. But it is what I mean. If you can drill on it, you can imagine that this is a fold or an anticline, which is a very good structural trap. So we have two types of multiples. Multiples is a type of the coherent noise. We have two types of multiples: short period multiples and long period multiples. The short period multiples affecting the coherency of the data itself, but the long period multiples generate fake reflectors on your seismic data, and because of this, it is very dangerous actually. So let's see this example to understand how processing increase the signal to noise ratio or remove the noise by any sort. If you take a look on this part of marine seismic field record, can you recognize signal from noises now? Yes, some of you noticed that. So this is after the processing. Now you know that what are the difference between signal and the noise. Do you want to see what I'm removed from this? This is all the noises. So if you add this one, the noises, the difference plot to the data after cleaning or after processing, you will come up with the beginning. So this is how we get rid of the noises, or how the noise looks, and how we remove or get rid of the noises. So if we try, we see this now on field record. Let's see it on the stack. You see this stack? Yes, you see some reflectors. This is a vertical section. You see some reflectors, but they are not clear. After processing, when we increase the signal to noise ratio, this is how the section looks like. Okay, much cleaner. You can follow up the reflectors very clearly. So let's go to the seismic processing flow. We will understand what are the basic seismic data processing flow and how we build this processing flow and test the parameters. So these are some processing routines, the names of some processing steps or routines. So we load the data from the field that came on magnetic tapes, yes, and then we reformat this data to the processing software format, and this is this step called demultiplexing. Okay, and then we will put the geometry. What is the geometry? The geometry is as we mentioned, this is a split spread. This is an off end. We have to know the XY. If you remember from the last lecture, the navigation parameters, the XY for each receiver, the XY for each source. What are the offsets, the distance, and so on. These are all the geometry, and it is critical and very important. And then we do a step called editing and a step called demuting. We'll see all of these now. To do the geometry, as I just mentioned, you have to know the navigation from the field. Then we have some sort of processing steps like amplitude correction, frequency filter, deconvolution, CMP sorting. I think we mentioned something about this when we talk about the functions of the processing. You remember? Okay. And then we could talk about velocity analysis and normal move out correction. This is followed by stacking, which gives me the stack section, migration, and post-stack processing. I can output data from here to disk or whatever media. I can print and see the sections, or after the post-processing. These steps, we called it in the industry, we call the pre-processing steps. And these steps from the very beginning up to the normal VAT correction, we call it pre-stack processing. And after the stack, these steps, we run the processing in the short domain. And after that, and this is in the CMB domain, so you see the name conventions that we use. So we have pre-processing, and then pre-processing, you have some of the processing steps applied in the short domain, okay? And you have the pre-stack processing, in which you can apply the processing on short domain or CMP domain, and then you have the post-stack processing. We will talk about nearly each step of this in the real data examples to understand what we are doing there. So how I choose these steps? So I'd like to pay your attention to that. There is no standard processing flow, you know. So I myself can process the data today with a certain processing flow, and after several days, when I take a look again and try to identify the noises and signal, I may add or remove some of the processing steps. So how we choose the parameters for the processing steps? We use the testing. So for example, if I have the raw data, I have the tape or disk that has the field data, this is what we call the raw data. And then I start to apply a processing step. In this processing step, I put different parameters. We will understand this in the examples. So suppose that I use 4 different parameters for this, and I did find that the parameter number 3 is the optimum one that gives me the geological solution of this, or the right seismic reflection. So I will put this parameter 3 and go to the next step and run some other tests or changing the parameters and choose the best of them or the optimum, and then finish with my data and out my data and type it to or store it to tape or disk. For example, if you see this is a part of the seismic section, if you take a look on the red circle and you have a reflector in the yellow dashed reflector, you will find also a synclinal shape, which we call the seg. Okay, so we have a sag here. But if you take a look on the shallowest part of this section, you will find a shape of the synclinal shape. This is the shape of a channel. This is a channel on the surface, and the channel on the surface is full of mud, which has a very slow velocity compared to the surrounding rocks, which because of that, this reflector came later in time than the others or the surroundings. Okay, so after at the first test and parameter, we corrected. So now it appears straight, but you still have bad data on the deeper part. So after that, in another step, you can improve the data in the deeper part and so on. So each one or each problem you see or each type of noise you see, you can change what I mean or attack with certain processing step with different parameters you have to test. So let's end our session with a real data example to understand what we were talking about now. So we'll give examples of the demultiplexing, the trace editing, trace muting, the geometry, the static corrections, amplitude corrections, frequency filtering, deconvolution, spatial filtering, the multiple attenuation, the normal void correction, and the seismic data migration. So the demultiplexing, as I mentioned several times today, is changing the data from the field digital format into the processing software format. So again, if you remember this picture, these are the tapes that contains the reflections that or the acquisition of the data we acquired or recorded in the field. Different types. Part of them are very old media and part of them are recent. Then if we dump what's written on this, which is the format, you will find it is numbers sorted by certain shape, which are the feed format. The demultiplexing convert this back into the sort of waves or the analog, if you remember. Okay, and it gives me the sort of field record as you see here. So now let you check yourself what you see. What record is this? What's the geometry of this record? How this record were acquired in the field? Does it off end or split spread? Where is the source position? Where are the different receivers of this? So this is a split spread single record. Okay, the source was here in the middle. Okay, so this is mostly land acquisition. Okay, mostly. So now I have the data. I plotted in which domain this is this. Which domain is this? Yes, this is the TX domain or the time domain. So now I reformat or demultiplex the data and plot it in the time domain. Why? To see the difference or to identify where are the noises and where are the signals to do the sort of corrections and enhance my data. So going for trace editing, if you take a look on this record here, please take a look on the traces. Have you find any odd trace? This is generally good. Actually, there is one or two bad traces, but for you to know how to differentiate between bad and good traces, please take a look on this part of the record that have zoomed on it. So good trace is a trace that has the reflections at different times, but bad trace is any other trace that contains whatever spikes, whatever a different shape than the other trace. So this what we call bad traces. And so trace editing is to remove the bad traces from the data. We can do this, what I mean, manually. So you can go and click by your mouse on the bad trace and apply the editing. We call interactive processing, or we can use that using the software itself, the processing software. So let's take a look on this part of the seismic record. Have you recognized where are the bad traces and where are the good traces? Yes, these are the bad traces. So what is or what does the trace editing routine remove, how it removes this batteries. It very simply, it multiplied by 0. It's zeroing its amplitude. So when you apply the editing, you will end up with traces, empty traces that don't have any of the reflection. So simply like this. So you can do this again interactively by you recognize by your eye and edit the data, or we can use automatic editing in which we identify to the software amplitude thresholds. So we ask the software, if you find the amplitude very high than this threshold or very low than this threshold, please multiply this trace by 0. The next or the third step is the trace muting. And in trace muting, we just, if you take a look on this sort of data, do you know where is the part that contains the reflections and where is the part that doesn't? Yes. If we go like this, this means that we want to remove this part. This is what we call the mute. So we digitize a line on the top of the reflector, the shallowest reflection, and ask the software to remove all above it. If I remove all of the above it, we call it top mute. If we remove all fluid, we call it bottom mute, and so on. We'll see another time. So, and this is how the record looks after mute the data. So we're in this mute example, we remove, it's called the top mute. We remove the shallow noises. We just cut it. Okay, we cut it. We multiply it by 0 again, like the edit, but this is on an area. Okay, so if you see this sort of record, can you recognize where are the noises and where are the signals? Yes. So the shallow part, we need to remove the shallow part, because these are refraction. If you remember the noise records that I showed you, we want to remove this refraction and direct arrivals, because they don't have geological information. And also you have this sort of noise. You want to remove this. So this is after muting, after processing, and we call this one above the red line is the top mute, and the other one we called it the surgical mute, because I surge or I cut part from inside the data itself. So this is how the mute work very simply. In the geometry, very simply, you have to know, you have to collect from navigation all the information, like again, the XY, the elevation, the distance from the source, and all of these were written in sheets or digitally, as we mentioned before. And if I zoom on this, you will see that the trace number, so the offset is whatever, the X offset is so, the azimuth was so, and so on. So these are the navigations that we use, and the geometry is very important to be able to sort the data in different domains. So to sort the data in different domains, you should have the correct geometry. And the most important sort is the CMP gathering, if you remember. Then we'll come to type of correction, which is called the static corrections. And static corrections, we apply the static corrections for one or the 4 reasons that I will mention. If I have difference in elevations between the receivers, if I have weathering layer, you know that the rocks, when it exposed to the surface, it weathered. So we'll have a weathering layer, and this weathering layer has thickness and also has a velocity affecting the velocity of the sound waves within this layer. So to have different, so I apply static corrections to compensate for differences in elevations, for the weathering layer thickness, weathering layer velocity, and refer all my data to a datum or a datum, as you see here. So as if I acquire the data below all of these elevations, and all of them are referred to datum. we have a lot to talk about static corrections. There are books for static corrections, but I'd like to show you real examples to understand it well. So if I have these two sections, they are two different sections, one in color scale and one in black and white. You see the arrows, the yellow arrows. So you have a sort of fold here, but it is intersected by faults. It could be false, so it could be faulted. And if you take a look on this black and white section, and you see these two reflectors, the darker reflectors, you will find them dissected. So I should have faults here. This is what affecting my data. No, this is not the reality. This data does not have the static corrections applied to it. But when I apply static corrections, this is what you end up with. If you go to this black and white section, you see the reflectors, how continuous the reflectors. There is no faults at all. And if you go to this section, you see that the fold is continuous. It is not affected by faults anymore. So if I don't do the right processing, I may end up with a fake subsurface structure. Okay, so this is how the static correction works. So let's talk about some amplitude correction. The amplitude is how the data appears. The reflections appears to me when I plot it in the time domain. So if you take a look on this record, you'll find it black, dark black at the early time up there, but you can't recognize any reflections in the down or the later time. When we do a gain correction, we redistribute the data. We know why the energy decays, what are the reasons for the energy to be decayed away from the source. There are different reasons. We call one of them spherical divergence, intrinsic attenuation. We have several things, but here I'd like you to understand what you see. You see the effect, and we can, in more details in the processing, we can talk very long lectures. So here, the reflectors appears. We do corrections here. Any step, I called it correction, is a processing flow, so it is mandatory to apply it. Mandatory to apply it. Any step called correction, it is a mandatory to be applied in the processing flow. So this is the gain correction, or sometimes you hear it, the spherical divergence correction. We have another amplitude correction, so we call the automatic gain control, but automatic gain control is artificial. I calculate the amplitude differences from the data itself. So if you have this sort of off-end record or marine record, you see that the reflectors are darker on the early time and faint here. You can see any reflectors here. When we use this AGC or automatic gain control, you start to see reflectors here. You can change that. You can even improve that more. You can see it like this. You can see it like this. Here is the parameters when we took. You remember that the parameters I took in the test. So here is the different parameters are the window of calculating the correction amplitude. Okay, so if the window is decreased, you will end up with a very, very hot appearance of the data. But you see that this shallow part, okay, again, which is not data, it's noises, also appear strongly. How can you remove this? Yes, with the top mute. Okay, so let's talk domains of the frequency. So if I have these sort of records, I have 4 records beside each other here, and this, can you see any reflections? No, you see some lines, what I mean, cover the whole. Convert this in the frequency domain, this is how the data looks. So you have part with the reflection, you have part of the reflection appear here, and you have some noises are here, and this is well noises from the marine acquisition. So after you correct that, this is the frequency that I need. So I remove the other and return back to the time domain or the TX domain, and this is how the data. Believe me or not, but But this is reality. This is real data. So on your left-hand side, this is how the data looks before processing, filtering, just filtering. And in your right-hand side, this is how the data appear after filtering. Going further to the deconvolution, which what we do is the deconvolution. What are the function? Yes, it is enhancing the data in time. Okay, so we enhance the data in time. So deconvolution affecting on the data by sharpening the reflectors and removing the short period multiples. Okay, so two functions for deconvolution. One of them we call the spiking deconvolution, which sharpens the reflectors, and the other one is a predictive deconvolution, which removes the short period multiples, which is type yes of random noise. So if you take a look on this seismic section, the seismic section looks very good. We have a lot of reflectors, but how about the shallow part? Okay, if I apply deconvolution, you see the result. Continuous reflectors, very sharp and clear appear for my eyes, and also the shallow section is much better. So you increase the signal to noise ratio. So going for the spatial filtering, or which is a linear noise attenuation, you remember the second domain, which is the FK domain. Yes, we have this data. You see the primaries or the reflectors here are mostly flat, and you have some linear noises. This linear noise, we attacked it by the FK filter. So we convert the data by the forward Fourier transform into the frequency domain, plotted in the FK plot, and then it choose the data around the center, which is flat. If you remember the example I showed you in the domains, this is how the record looks after the FK filter. You have more continuous reflectors, and the linear noise mostly disappear. Going to the multiples, and I remember that we mentioned that deconvolution get rid of short period multiples, but we can use the parabolic tau b, for example, to remove the multiples. Do you recognize the reflections here? Yes, you have a lot of reflections here. No, I'm sorry, not all are reflectors. Some of them are rare reflectors, and others are echo, which is we call the multiples. So you see this is the water bottom. It is repeated several times. When you apply the multiple attenuation processing step, you remove most of these reflectors. Don't worry, they are not reflectors. They are fake reflectors came from the echo, or this is what we call the multiples. Then we go to the technique of our data, which is we gather the data into the CMB domain to gather them, to stack them. This is a technique, if you remember. And this is the geometry of the CMP. So if I have the CMB gathered like this, so I will end up with the reflectors that has this hyperbolic shape. And why I have this hyperbolic shape? Because the far traces receive the same reflector at later times than the near traces. So the job that I want to do now, I need to gather this data together, because it represents only one subsurface point. Okay, so how I can solve for delay in time, which is delta t, with the distance, the offset. What tie between time and distance? Yes, the velocity. So I try to find out the best velocity that can correct this hyperbolic reflector to be flat. So using the velocity to calculate the delta t. In other words, how I do this? I do this by velocity analysis, and this is what we call semblance. And here we pick the best velocity that correct this hyperbolic reflector into flat reflector, because at the end I will stack them, which means that I will gather them into only one trace. and one trace beside one trace beside one trace give me the seismic stack section. So go to the last and most powerful tool in the processing, which is the seismic data migration. Again, seismic data migration, you have books, you have different types of migrations. We have time migration, we have depth migration, we have different algorithms to the migration, like the Kirchhoff algorithms, we have the finite difference algorithm, we have the RTM, we have the pre-stack depth migration, the post-stack depth migration, lot of things. But what I'd like to show you is what are the effects of the migration? How the migration enhance my seismic data? If you take a look on this seismic section, please concentrate on these parts. What you see here, you remember? At the very beginning of the lecture, you have, yes, these are the bow ties, okay? It's like you tie something together. There is no geologic feature like this, okay? So when I apply migration, you remember what are the reasons for that? Because of these are synclines. So when I correct the data, it gives me the correct subsurface. If I have, like, you see, have you seen anything here? You have reflectors, what I mean, interfere with each other. But this is unmigrated section. It is processed, but unmigrated. We don't apply migration for this one. When we apply migration, this is how this reflector looks like. These are real data. These are real data. And so on. This is another example. You see how this anticline is wide, but when you apply the migration, you find it smaller. What I mean, shrink, because this is the reality. Okay, let's see more example. So if I have like salt dome, so you have salt dome here, but you cannot see what I mean, its wall perfectly. But after migration, you can locate it like this. One of the main factors for the migration is the velocity model we use. And you know that what I mean by velocity is the sound wave propagation velocity. So if I imagine how fast the seismic waves or sound waves propagate through the subsurface, I can, what I mean, migrate the data very well. So you see how the velocity model looks. It looks like the structure, actually. Okay? So the migration is the most powerful tool, and we can apply this in the pre-stack domain, and you understand now what's pre-stack, or in the post-stack, I can apply time or depth, or with different type of algorithms. Okay? So, for example, if you see this section, you have very good section, actually, and we apply pre-stack depth migration to this. You see this salt body here, but which one is better? Okay, which one is better? So this was processing in 2010, this Kirchhoff processing in 2015, this is another processing on the 18th. Okay, so you have a lot of improvement, enhancing the data. So this is how the processing affecting the data. With this slide, I conclude my presentation to you today. These are my contacts, and I will be happy to receive your questions. Thank you.
Thank you, Dr. Hatem, for this amazing session. Thank you very much. We shall now address the questions received. First question is, what's velocity sensitive detector and how it is work?
What velocity is sensitive?
Detector.
So the velocity detector, or what? I'm sorry.
Yes, what's velocity sensitive detector?
Okay. The velocity sensitive detector is the geophone, which is what I mean, sense the mechanical movement of the particles, the raw particles. So it counts the velocity, which is what I mean. So it is type of G form.
Okay, second question is, how can I distinguish between sorting and gathering?
Okay, we sort the data and collect them. We sort the traces and collect them into gathers. Okay, so sorting is a mechanism, or is the what I mean, the mechanism, yes, of what I want to do, and the gather is the ensemble that I put the traces on it. So
Okay.
sorting is a process, and the gather is the final product of this process.
Okay. So third question, can coherent noises be eliminated or reduced by using same methods that are used for random noises?
Yes, of course. What we mentioned is how we eliminate or reduce the coherent noise. So, for example, the filtering can remove both random and coherent noise. Okay, but for the coherent noise, for the random noise, actually, it depends on the activities around the acquisition. So I may delay my acquisition to another time, just to eliminate this random noise. But random noise can be removed easily by stacking, which is a mandatory processing step, or by filtering. For some of them can be removed by filtering, like the ground roll. I can use filtering to attenuate the ground roll. But for example, for the multiples, I will use different techniques like the tau B, parabolic tau B domain, or I can use FK, or I can use stacking also for the multiple. So different types of.
So last question is, can we use multiple attenuation process many times to eliminate all the multiples?
Of course, yes. We can use different types of multiple attenuation techniques, because multiple attenuations depends on different, what I mean, criteria for the seismic. For example, it depends on the periodicity, or the velocity discrimination, or the depth, or different types. So actually, multiples are very bad, because of that we use several demultiple techniques to get rid of the multiples, and you will end up, believe me or not, the final output will still contain some sort of multiples.
Okay, that's pretty much it for the questions. Thank you very much for your time and efforts, Dr. Hatem. And we hope to see you next week. Final reminder for everyone, this session will be published by Dr. Ahmed Al-Garhi on Facebook page, Arab Oil and Gas Academy. And please make sure to submit the quiz before the deadline. And see you next week, hopefully. And stay safe, everyone. See you for the next time.
See you. Bye.
Thank you. Thank you very much, doctor. Bye-bye.
Bye-bye. Thank you.